Hi, welcome back. So I hope the things that we have discussed till now like gradient descent, linear regression, polynomial regression are absolutely clear. Okay. So now I want to discuss another algorithm, that is logistic regression. Now the name might suggest that it is a regression algorithm, but it is not. It is used for classification problems. Okay. So this is a classification algorithm. So what are classification problems? The problems which have their output variables, that is y, as fixed classes. Okay. So let's consider an example. We have a problem, we have lots of images of cats and dogs. We have to predict which image is of cat and which is of dog. Let's say for cat we say that it is class 0 and for dog we say it is class 1. So obviously some images are going to be class 0, that is some images are going to be of cats and some images are going to be dogs. Okay. So this is what my data set might look like. So clearly this is a classification problem. So logistic regression we use for classification problems, and another feature is we generally use logistic regression for binary problems. Yes, there is a way how we can use logistic regression for multi-classes also. Yes, there is a way how we can use logistic regression for multiple classes also, that we will discuss later. But as of now, just consider that logistic regression is for binary problems. Okay, that is binary classification. Now, how do we do that? Going back to linear regression, what we actually did there was we tried to build a relationship between x and y that was basically a line. Okay, that was basically a line. The equation was mx plus c. Okay, the equation was mx plus c. In machine learning terms, we call this function as hypothesis. So hypothesis function for our linear regression was hx is equal to mx plus c. Okay. Now this line, as we know, there are infinite points on a line, so there are infinite possibilities for our predictions. Okay, infinite possibilities for our predictions. So y is equal to mx plus c was the hypothesis function that we considered in the linear regression. Now in logistic regression, we will have to find a function which gives me only two values, that it should either give me 0 value or it should give me value of 1. Okay. So we have to go back to mathematics and we have to bring out a function which generally gives us two values, that is 0 and 1. So for that purpose, we have a function known as sigmoid function. We have a function known as sigmoid function. Okay. So I hope you realize the importance, why we need this function, because in linear regression we wanted that our output should be able to take any value. Okay, should be able to take any value. So in linear regression, as we know, a line has multiple points, so we took a function such as that. Okay, so I hope you realize why do we need such a function. Basically we want for each image I should get a value either 0 or 1, according to which I will be able to predict whether it belongs to cats or it belongs to dogs. Now what is sigmoid function? The sigmoid function basically is sz is equal to 1 upon 1 plus e to the power minus z. Okay, 1 upon 1 plus e to the power minus z. For our purpose, we are going to write hx is equal to 1 upon 1 plus e to the power minus gx. Okay, so basically our hypothesis function is 1 upon 1 plus e to the power minus gx, where gx is going to be m1 x1 plus m2 x2 plus m3 x3 and so on plus c. So this is going to be my gx. Okay. So if I plot a graph of this sigmoid function, it looks something similar to this. The graph between hx and gx, it is going to look something similar to this. So this is going to be 1, this is going to be 0, this is 0.5. Okay. So for any given gx, I will generally get an hx which is very close to 1 or which is very close to 0. But for some of the in between values, like let's say these values, I am going to get an answer which is like little farther away from 0 and 1. Okay, but for most of the values I am going to get my answer which is very close to 1 or it is very close to 0. This function very quickly reaches 1, okay, and very quickly it reaches 0. So this is the function that we choose. Now let's say for a given gx, that is for a given image, I am getting an output of 0.99. Okay, so class 1 is my dogs and class 0 is cats. So for given gx I get an hx of 0.99. I would very clearly be able to say that this image belongs to dogs. Okay, this image belongs to dogs. If I get 0. Let's say 0.2, I would say that this image belongs to cats. Okay, that this is an image of a cat. So I can say if gx is greater than 0 or hx is greater than 0.5, then I would be saying that it is class 1. Or if gx is less than 0 or hx is less than 0.5, it belongs to class 0. Okay, class 1 is our dogs and class 0 is our cats. So this is how we can use logistic regression to basically classify. Okay, so what do we mean when my algorithm say that 0.98 value? When it says that hx is equal to 0.98, it basically tries to say that I am 98% confident that this image should be an image of a dog. Okay, or if it gives me 0.75, it is saying that I am 75% sure that this image is an image of a dog. If it gives me 0.01, it means it's saying that I am 1% confident that this is the image of a dog, or I can say I am 99% confident that this is the image of a cat. Okay, so 0.01 would mean 99% confident that it is the image of a cat. Okay, so basically as close to 0, it's more and more confident that it is the image of a cat. As close to 1, it is more and more confident that it is the image of a dog. Okay, so I hope this thing is clear. But if it gives me a value of 0.55, it says that I am 55% sure that it is the image of a dog, and 45% I have doubt that it might be image of a cat also. So in this case, if we have to predict, we obviously will be predicting dog, but our algorithm is not very confident. Okay, like what are the cases it might happen? Like there are few breeds of dog which might actually be looking like a cat. So in those cases, our algorithm might be confused whether it is a dog or a cat. So it might not be showing that much of a confidence in itself. Okay, so for the cases when we have like a high value which is like above 0.9, we are like very confident that our algorithm is predicting correctly, that is, it is predicting dog. Similarly, if we have like a small value like 0.08, 0.07, it is very confident that it is image of a cat. Okay, but for the in between cases, let's say 0.6, 0.4, 0.45, 0.56, it is not very confident. Okay, so I hope this part is clear how we can use logistic regression for classification. We are basically using sigmoid function. Okay, so one last thing that I want to discuss about this is the cost function. Okay, the cost function. So if you remember, in the case of linear regression, my cost function looked something like this. Okay, so this is what my cost function looked like, or I can say mx plus c is my hypothesis, y minus hx square and summation of n. So similarly, in the case of logistic regression, my cost function should something like this: 1 minus 1 upon 1 plus e to the power minus gx square summation 1 by n. So ideally, by logic, it should be something similar to this. But this is not what we take. Okay, this is not what we take as our cost function for logistic regression. There is a very simple reason for that. The graph for such an equation is something similar to this. Something similar to this. Now, what the problem we have with function similar to this is that if we try to apply gradient descent on this, let's say we take any value of m, let's say it lies over here, m naught. When we apply gradient descent, we will try to come down and we will reach over here. Okay, we will reach over here. But is this the point where we want to reach? No, this is not the point where we wanted to reach. We wanted to reach this point. Okay, from our whole graph between cost and m, I want to reach the point where the cost is minimum. But in this case, I am reaching this point. So basically, I am reaching one of the local minima. Where do I want to reach? I want to reach the point which is the global minimum. Okay, I want to reach global minima. So we are going to consider only those functions which has only one local minima. Okay, which has only one local minima. We won't take any function like this which has more than one local minima. So we want a function something similar to this. Okay. So for that reason, to get a function which has only one local minima, we take the cost as, cost for logistic regression is minus yi log hx minus 1 minus yi log 1 minus hx. Okay. So this is the function that we take as the cost function for our logistic regression. Obviously, there is going to be a summation over here for all the i's. Since this function is a function something similar to this, so we are going to accept this as our cost function, so that gradient descent is a good idea to be applied on this. Okay. So I hope you are clear with logistic regression and how we can use it. So in the next session, we will try to apply logistic regression. Thank you.